today we're, hopefully finishing up 7 and starting 8, because we still do have one more day to work on this on Friday before our exam on Monday. And other than that, we have one regular computational homework due tonight and the first half of discussion 1 due tomorrow night. All right. So what were we up to last time? Well, in parts 6 and 7, it pretty much started with this exact same calculator that we talked about last time for part 4, where the main difference was I just changed this purchase date to 1/3/2000, and we're done. So as long as you're using references, it's the exact same steps. So if you've forgotten any of these steps, check out the lecture from yesterday. I go through all those there. Now, the second question is a little bit different. It starts the same as the problem we just did. We buy in 98, we sell in 99, but here's where it's different. We take this $53,445 that our 10,000 becomes, and I drew a little arrow, you don't have to do that, but we take that and we reinvest it and start this whole process over again. So as you can kind of see, it's the exact same calculator twice. So we take that 53,000, we reinvest it. We wait all the way to 2017, same exact steps, should turn into about 2.8 million. Now, there's a couple other follow-up questions about like unspent money. That is a little bit different. What's it talking about? Well, for example, initially we had 10,000, but we only spent 9,971. So the difference, what's left over, was unspent, and then they have you carry that work forward to finish up some of those questions. Now, in part 7, what we were doing was taking these 10 dates that they gave us and investing $1,000 at a time, and just taking these 10 separate investments and sort of doing the same things we've always been doing. Just tracking them, see how much money we spent, see how much we bought, and then having some final investment all the way down in 2017. So we look up the close price using XLOOKUP. We figure out the shares by seeing how many times the close goes into the amount of cash you have and not forgetting to round down. And then they also wanted us to have like a running total of shares. So at first it's just the same number, but every cell past that is what you had the previous year plus what you're adding that particular year. So by the end of these 10 years, you have 336 shares when it's all said and done. And spent is, again, same calculation from part 1. If you buy 72 things at this price, how much money is that? And it's always slightly less than the amount of cash you have. Then follow-up question, what's this worth in 2017? And can you just multiply these 336 shares by the close price? So yes, you can just multiply these 336 shares by the close price, because all of the stock splits happened from 1999 and before. So if we're starting in 2001, there aren't any stock splits we have to worry about. So these 336 shares stays 336 shares. We just need to multiply 336 shares by the price of one of them to get the final value. And to get total spent, we can use that little sum function we haven't used in a while to add those up to get that number there. Now, the only input to this whole calculator is that guy. If you change this thing, all those numbers change accordingly, which is really nice. You are never going to change those dates. So do not mess with those. Likewise, we build the exact same calculator using these dates in July. It's always a good idea to have these two calculators separate, because that way you won't have to go back and forth plugging in these 20 dates. You can just reference either your January calculator or your July calculator. And that was the main idea in part 7. Now, what we're doing today is the final part of this module. And so I'm going to move into my notes to introduce a few concepts here. So first thing I want to talk about is an example we've actually already seen, just to introduce what's going on here. So This is an example, I believe, from the part 0 homework from this module, where we had some $500,000 house. The value was going up by some percent every year. What's it worth 2 years from now? So in this case, I'm going to go up by 10% a year. So I take my 500,000, multiply it by 1 plus 10%. That's what it's worth at the end of year 1. Now, what about the end of year 2? Well, we take that value we just found at the end of year 1, we increase that by 10%, and then finally, that's our number at the end of year 2. What I want to point out is that is not the same thing as just increasing by 20%. So that percentage we have, you don't just take it twice for 2 years and double it and go 20%. That would just give us 600,000. So how can we simplify this process? Well, if I start with this last step and I write it again over here, we can actually expand the 550,000 because we have an equation for it right there. So if I replace this 550,000 with this equation up here, the formula actually becomes this. And now you can kind of see, oh, there's 2 of these sets of parentheses that are identical. And so the actual way to do this in one step is not to double the percentage, but to use an exponent. And that's how we simplify when we're multiplying 2 things together that look the same. And that leads us to a new formula, which is if we're increasing some number by the same percent every year for t years, it's the same formula we've always done, but we tack on a little exponent t on the end. Okay, so that is going to be really useful for part 8, and I'll show you why now. Now I'm going to introduce the concept of compound annual growth rate. Here's the idea. Let's say we look at the last 20 years of stock data. It's that blue line right there. Those are the adjusted close values. It's all over the place. It's up and down. You cannot predict where it's going tomorrow, let alone 1 year from now. I mean, it's probably going up, but you don't know how it's going up, right? It's going up and down all over the place. On the other hand, if you sort of smoothed it out and got this sort of average line, see that orange guy? That orange guy is incredibly easy to predict because it just follows a pattern. So the idea of what we're doing today is, can I find the rate at which that orange line is growing? And the rate at which it's growing is called the compound annual growth rate. And that has to do with the previous formula we were just talking about. So let's say I do know the formula for that line. What I can do is say, oh, it's just going to keep following that pattern. I think, you know, the stock price will be here a year later, something like that. That's our goal. So anyway, if I want to find that compound annual growth rate, I can actually take that formula we just wrote down and solve this for P. Because remember, P was an annual rate at which some number was growing. That was the number we want to know. And more specifically, the numbers that are growing were adjusted close values. So I'm going to rewrite this for a second, saying I'm going to take some old adjusted close value. It's going to grow some annual rate, and I get some new adjusted close value. If I can solve that for P, that's the compound annual growth rate that I want to know. So we hit this with some algebra, and we get this guy. This is the CAGR, the compound annual growth rate. It's the same thing as that P right there. And that is one of the other things we're interested in solving today. So that's 2 new formulas, and I'm going to do a couple examples with you right now, showing you how to use each. Okay, so before I do those examples though, let's do one example first, and then I'll introduce this other concept. So let's say I have these 2 dates. I look up the 2 adjusted close values from my historical data. There's my formula. I know that they're 2 years apart, so I can literally just see it. Well, if I plug everything in, just like this green formula is telling me, if I take the new adjusted close over the old adjusted close, little caret raised to the 1 over 2 years minus 1, I get a compound annual growth rate of 41.42%. So what that's saying is if I start at 200 and I grow by 41% each year, then 2 years later, I will stop at 400. And we can actually check that, right? By plugging it into that other formula right here. So if I take 200, I grow it by 41% for 2 years. I do in fact get it 400. So that's what the compound annual growth rate is. That's one type of example where we're solving for. Now, that's not technically what we're going to be doing with that formula, but I just wanted to show you what it looks like when you plug those things in. What we're actually going to be doing is more like the next couple examples, but I need to introduce something else first before I do that. So in the previous example, the dates were really nice. We just looked at these dates and we said, oh, they're 2 years apart, easy. What about these? How many years apart are these dates? This is significantly harder. I can't do this in my head. We need some actual math. And the way we're going to do this is use the fact that Excel stores dates as numbers. Remember how sometimes these dates look like that? Well, one of the reasons is because they're just numbers, you can do arithmetic on them. So check out this cell right here where I'm computing days. If you literally just subtract dates, it will tell you the number of days in between. Okay, that's good, but I still want years. So I can use this conversion right here in green to do one more step. I divide the number of days by the conversion rate, and I get that the amount of years between those two dates is roughly 0.539 years, an exact value, which is really nice because if we're getting different numbers, none of our answers are going to agree. So let's actually start that first problem over again with this new method. So we have these two dates. I start by taking the future date minus the past date. That's how many days are in between. I take the number of days, I divide by 365.25. I get that it's almost 2 years, but maybe there's a leap year in there or something, but slightly off from 2. I plug it into that green formula by doing new adjusted close over old adjusted close raised to the power 1 over years minus 1, literally just plugging it into that formula. And there's our CAGR. Now, small problem. This answer, same example, different from this answer. And the reason why is we used a different number of years, right? This was years 2. This was slightly more than 2. So which one is correct? Well, I would argue that they're technically both correct. Just depends on which method you use. But for the homework questions and exams, the dates that they feed you will always look like this. And you're not going to be able to just say, oh, they're 2 years apart, like this example. So while you're working through the problems in the workbook, I would strongly suggest you practice what I would call the messy way, not the whole number way, because the messy way works for any pair of dates. Okay, so yes, there are 2 answers, but on the homework and exam, there will only be 1 because you have to use this method. Okay, so that is how to find the CAGR. What do we use the CAGR for? What's the point of finding this number? Well, the whole point, remember those graphs I showed you, was to project into the future what we think the stock price might grow to. And in order to use that, we're going to use the other formula. So let's try this really quick. What do we need to know? We need to know the old adjusted close that we're starting with. So I pick a date, I find the adjusted close. We need to know the percent that we're increasing by. That's going to be the CAGR. And we need to know the number of years. Okay, that's the only thing I don't have so far. So what I'm doing is I'm continuing this work from before. I already know the CAGR. I'm going to take that second date. And now from this date, I'm going to compute how many days have passed. How many years is that? And then I can plug all this in to project what I think it'll be if it grows from this date to this date, just to make one possible prediction of the stock price. So I can take my 400, my old adjusted close, I multiply it by 1 plus the CAGR, I raise it to the number of years. And even though it was $400 for 1 share back in 2017, if it grows at this rate, I think it's going to be $988 in 2019. And this date has already passed, so we could, actually see if that was the case. But it is just a prediction, so it's not necessarily going to be always correct. But it is one way to project out into the future. If I want to know what the want to make a prediction about where I think it'll land in 2025, that's one way to do it, or at least model one possible price for future value. Okay, so that is how to come up with these numbers that we're sort of jumping into the future. The other thing I want to talk about is how to make this graph, because that's also in part 8. So we're trying to make this graph. The blue line is very easy. You graph column A, the dates. You graph column G, the adjusted close, done. That's blue line, easy. But the orange line, the smooth line, you are going to have to build these numbers yourself. You're going to have to use that formula to project, some adjusted close into the future. So it grows at this smooth rate. And then you're going to have to add this curve to the graph. Okay, mathematically, we know how to do that. We saw the formula. However, this does require us to learn a new graphing technique, and I'll show you why. So let's say we had these x coordinates and 2 pairs of y coordinates. This is very easy to graph because you just highlight them all. Let's say I want to make a connected scatter plot, and you're done. You highlight them all, you click the button. That is easy. We know how to do that. This is what's going to happen today. You're going to have one pair of points over here and another pair of points over here. They're not even the same size. Some of the x's don't even match up. So you can't just do a single selection. You kind of have to deal with these things separately because it's going to look like this. You're going to have your little table that you make that looks like this. And then that's going to have to get paired up with all 5,000 days in the data set. How do you do that? So let's see how we graph these two things. I'm just going to follow these steps over here. So I did write them down, but let's go through them together. Step 1, just pick either one and graph it. And these tricks only work with scatter plots. So I'm gonna graph this as a connected scatter plot, and I'm gonna pick one of these 5 options, specifically these two. See how these two do not have dots on it? I'll show you why. It gets kind of fuzzy. See how it's kind of, I'll show you the difference. That one versus, pick one of the options without the dots. This one's just much cleaner to read. So we graph one of the curves. How do I add this one next to it? Well, you make sure you're selected in the graph, and up at the top of your screen, you should have a button that says chart design. Then in there should be a button that says select data. And what we can do, we can see our original curve. We can hit this add button here to add a second line. If you're on Mac, it's going to look a little bit different. You're going to be looking for a plus symbol, also to add a line. So I click that, and it asks me, okay, what's the name? I can call it curve 2. That honestly, it doesn't matter. You can leave it blank. What are the x values? Easy, they're right there. What are the y values? Get rid of this thing. Easy, they're right there. Hit OK a couple times. There's our graph, has both lines on it. That's how you deal with the fact that these two things had some sort of size mismatch.